All right, so this discussion was a bit general and abstract. So let's see how it applies to some simple examples. And the first example that we look at is two-point functions. And I suggest it as an exercise in the most general form, but I will do a very specific example. So in a conformal field theory, you have actually let me do the thing. The two-point function has a very simple form, which is some. Did I use? Let's use capital G. Okay. So I consider the two-point function of two operators, phi k and phi l. So first, let's say that they are primary operators. And let's say that they are scalar operators, just to make my life easier. And the two-point function has this simple form. If the two operators have the same conformal dimension, then this is just 1 over x, the separation to the twice the conformal dimension. And I wrote delta k is the conformal dimension of one of the two operators. This is 0 if the conformal dimensions do not match. That's why I write this in this way. So why did I write this strange normalization thing? Typically, when you study correlation functions, you want to normalize the two-point functions canonically. And the obvious choice is to choose a basis where this is like the Kronecker delta. I think this was what was used in one of the previous lectures. But this is not always convenient or even possible. And the obvious example would be the marginal operators themselves. As you saw before, the marginal operators have a very well-defined normalization up to redefinitions of your coordinates. Their normalization is fixed by the meaning of delta lambda. There is no more freedom in rescaling these operators. So whatever we get on the right-hand side will be whatever we get. And in general, there might be other reasons why this normalization is fixed. For example, if these operators correspond to some currents of some symmetries, then their normalization is fixed in terms of how they act on the rest of the spectrum. On like the algebraic relations will fix the normalization of these operators. So we keep this particular quantity arbitrary for now, and we study how it changes when I deform the theory. Hopefully, we will learn that this is not really important if we deform the theory. It will be our first sanity check of this formalism. So what we want to do is to compute the covariant derivative of phi left x phi k 0. But this I will give to you as an exercise. I will do an even simpler thing. I will put this operator, instead of a generic point, at infinity. And why do I do that? Well, because you see from this formula that there will be, in general, two contributions to this change of the correlator. There will be a contribution that comes from the fact that this normalization could change as we move in our space of couplings, but also the conformal dimensions themselves could change. And in the language of standard perturbation theory, you would say that operators acquire an anomalous dimension. Right? So conformal dimensions do change as we change the theory in general, unless there is some magic protecting them or unless these are currents that are themselves protected. So what happens if I put an operator at infinity? Remember that the prescription is that I have to take my correlation function, and when I take the limit where x goes to infinity, I have to multiply precisely by this factor so that there is no more x dependence in the final result. So what this corresponds to is the covariant derivative of this object here. It starts to look more and more familiar, I guess. And so we are basically, The question is, could I have put this at 1? Yes, I could have. But then I would have, my argument will not be as clean, right? And this will have to do with these logarithmic ambiguities that you were mentioning before. So let me do it in this way, and this is going to be fine. Question? What? This? The thing that I'm differentiating?
Correlating from 0 to infinity.
Oh, this object here. Well, yeah, you see, so Sylvain explained to you that when we put, these correlators that I'm defining on the plane should really be thought of as correlators on the Riemann sphere, right? So you should imagine that you have a sphere, and this is my phi k of 0, and this is my phi L at infinity. In order to get something finite here, I need to, when I take this limit, and if I imagine of mapping the plane to the sphere equivalently, I have to multiply this object by x to the 2 delta k. So when I take the limit to define this object here, I multiply by this thing. And I will get precisely this thing. It's just a trick. But it's a trick that has interesting meaning, and we will explore this more and more. So this is the quantity that I'm computing, and I apply just the rules that I told you. So I had to compute this integrated correlator, OI, phi L infinity. Well, I'm using a bit of a annoying order of the operators, I guess. But the line? Yes, question. Yeah.
Depends on lambda, both left-hand side and right-hand side.
Yeah, so let me write more explicitly the possible lambda dependence of the object that I wrote in the first line. So this correlator is some correlator that we imagine depends on my coupling constants, and there are two possible contributions. The normalization might change with the coupling constant, and the conformal dimension might change with the coupling constant. These are the two sources. By doing this operation, I'm getting rid of one of the two possible contributions. I'm isolating. You can, of course, you don't need to do this. I'm just doing it for convenience, and so you have a nice exercise to work on tomorrow. So I do this, right? And I have to excise these disks from both 0 at infinity. So it means that my y will be integrated only from epsilon and a disk of size epsilon around infinity in the Riemann sphere is just in the plane a disk of size 1 over epsilon. This is the operation I have to do. And you know how the integral looks like, right? You studied it in the previous days. So this is just the structure constant coefficient, Ci k L, M G M L. Right, so I take the OP expansion of the operator OY with phi k. This gives me a sum over all the operators in the theory, and in the end I have to contract it with phi L. That's why I have this two-point function, because I'm allowing for an arbitrary normalization. And then the only y dependence is y to the 2 plus delta k minus delta L in principle, but these two are equal, so it's only 2. You agree? Yeah. So, you know, you can do this integral in radial coordinates, and you write this as dr, r dr, and okay, use a better eraser maybe, r square, right? So it's from epsilon to 1 over epsilon. So this will be, there is a integration over the the angular variable, but remember that I conveniently put 1 over 2 pi in my definition of the covariant derivative. I also put a minus, I think. So this will be equal to this. And you can do that. And there will be some number. So let me be proportional to C, I, K, M, G, M, L log of epsilon. Right? And then I apply my rule over there. I extract the finite part of this, which is 0. So this is 0. That's what my regularization prescription teaches me. And do we like this? Question, yeah.
Why was the renormalization scheme not important to the other conclusion?
Why is the renormalization scheme not important for this conclusion? Well, it is important for this conclusion in the sense that I'm telling you that the scheme that I chose has this property.
It's the same question as before. Suppose
Yeah.
you send epsilon to epsilon,
Yeah.
things like that.
So the worry here is, imagine that I had used balls of different size. Wouldn't this give me some finite piece? Yes, it would. This would be a different scheme. And this would lead to a different connection with different properties. Yeah. So what I'm showing here is that this connection, this scheme, is compatible with this particular two-point function coefficient that appears in the two-point functions, which is a very nice property. And what does it mean physically? Well, remember that you can think of these correlators, these two-point functions, as some in the state language via the state operator correspondence. And this will correspond to some inner product, Hilbert inner product of states. So what I'm showing you, which is by definition GKL, what this shows is that the connection that I'm defining is unitary. Of course, even in standard quantum mechanics, I can define connections that are not unitary and then work with states that are not properly normalized. And every time I compute correlation functions or matrix elements, I have to divide by the normalization of the operators. All that I'm telling you here is that this particular regularization scheme is manifestly unitary. It preserves unitarity. It's a very nice property. Okay? And then, maybe, can I erase this line? Sorry. So the question is, why do you call this unitarity, since GKL is not obviously a positive? Well, I'm working only with unitary CFTs. And in unitary CFTs, you can always show that this is a diagonalizable, it's symmetric, obviously, but it's also positive as a matrix. So it has only positive eigenvalues. And why? Well, the condition of unitarity is precisely what I just erased. And this better gives me a positive norm. If I don't have a positive norm in my Hilbert space, then still this connection would preserve the norm. But maybe I wouldn't call it, yeah, it wouldn't preserve the unitarity if it's not present already in the theory. Yeah, another question?
So I suppose that obviously requiring conformal symmetry also means that the vacuum expectation value of the operators that appear in the regular part are 0, right? Otherwise.
Oh, okay, very good. So this is, the question is, how do I ensure So if conformal invariance is respected, I should be able to show that the one-point function of the operators remains 0, because conformal invariance tells me that if I have an operator of a well-defined conformal dimension, except the identity, its one-point function should remain 0. Right, so I don't know if it is obvious, but it's a good question that you can try to do. You can try to do this computation during the exercise. Yeah, thanks. Okay. So let's continue. Okay. So this is a bit of a weird thing, this two-point function coefficient. But let me show you something very nice that comes out from this. Imagine that we consider the two-point function of the marginal operators themselves. So let me put L and K just to be consistent with my notes. So now this object has much more right to be named G. And the reason is that, remember that these O's transform as tangent vectors, or a basis of tangent vectors under reparametrization of my on my parameters. So that means that this transforms as a metric under reparametrizations of my lambdas, right? It transforms with the inverse derivative of the transformation function. And so it is symmetric. It transforms as a metric, and it satisfies this property. This really looks like standard Riemannian geometry. And indeed, this condition, this compatibility condition, allows you to compute, in this case, the connection coefficients for these particular operators. You can just compute the Christoffel symbols from these compatibility conditions. Do you agree? Because there is a question. The question is it symmetric? Oh, is this symmetric?
No, the connection.
Is this very good? So there are subtleties. So this is not true that from what I said, I can compute the connection coefficient. One problem might be the presence of torsion. So, or in other words, the connection coefficients might have an antisymmetric part. And this is true. And the only thing that I will tell you is that there is no, as far as I'm aware, general proof that this connection that I'm defining here has no torsion. There are some arguments in the literature, and that are, convincing or not, depending on how willing you are to believe certain things. But basically, there is no very good answer to this question. However, I can tell you that I will give you an expression for the curvature very soon. And you can compute the curvature in two ways, either the hard way, doing the integrated correlators, or the easy way, assuming that I can compute the connection, the Christoffel symbols in this way. And in the cases where you can do this, it matches. So this is a good consistency check. However, this is really a kind of a weak point of this construction. Notice that the possible presence of torsion only applies in the subsector of the marginal operators, of course.
There are not so many examples for which we can really compute, really like, not n equal to 4 super Young means, which is trivial, something serious.
Right, so the comment is, there are so many examples where we can really do this. So how strong should we believe of the generality of this consistency condition? Well, I agree. It's only like in very special supersymmetric cases where you can really do these computations in different ways. And so you might believe that maybe supersymmetry is ensuring that there is no torsion, but in the non-supersymmetric case there is torsion or something like that. This is perfectly valid. Fine, let's say that there is torsion. The only thing that we lose is that we cannot really write the connection in a simple way. So we don't lose much. It's just that In the cases where there is no torsion, this has a very nice geometrical interpretation. And in that case, we can really think of my space of parameters as being a manifold with a metric on it. So this kind of justifies why I draw this manifold a bit curved. Otherwise it wouldn't make any sense. Yes?
Excuse me, one question. When you computed those three-point functions, you made use of the OP with O with phi. But why does the result expand only over phi but not over O itself? The OP of O phi, it expands only over phi but not O itself.
So the question is about the OP expansion in the three-point function?
About, maybe the upper board.
In the upper board.
You use that OP.
Okay. In the upper board, I wrote the OP expansion of O with a generic insertion in the correlation function. If there was another O in the correlation function, then of course that would be, maybe I should have stressed this more. The operators O are just part of the spectrum of my operators, and I'm just singling them out because I want to deform the theory by them. I should have been maybe clearer on this point.
O isn't present on the right-hand side of the
Yeah. So this is the point that I didn't explain well. Sorry. So it's not like we have the phi i's and in addition some other operators. I'm using a notation where the O i's are just some special operators that I chose among my phi's. So they will appear. So the big index will also include the small index if you want. It's just my fault that I didn't make this explicit. But thanks for pointing this out. So hopefully this didn't cause too much confusion in the rest of my explanations. And let me now move on to the computation of the curvature. No. It's important. I need to propose an exercise to you, but it's an important exercise. The exercise is to repeat this computation with the operator insertion at an arbitrary point instead of at infinity. So you will now get the contribution from this possible change. And what I will ask you to do is to show that the derivative of the conformal dimension is simply given by this structure constant coefficient. And this equation looks a bit inconsistent because there is an index, an additional index on the right-hand side. I might fix it maybe by putting delta KL here. So what is this equation telling us? It tells me that the OP coefficient of a marginal operator with any operator in the theory controls how the conformal dimension changes. But you have to be, you also learn that if K and L are two operators of the same conformal dimension, then this OP coefficient better be 0 for this equation to make any sense. So this is another condition of marginality. It's our second condition. It tells us that you have to use a basis of operators such that the OP coefficient of I of the marginal operator with other operators in the theory is diagonal. And this might look strange, but I encourage you to open your old first-order perturbation theory textbooks on quantum mechanics, and you will see that whenever you do first-order perturbation theory, you will have conditions like that, whenever there is a degenerate spectrum. This is a very, very natural condition, just written in a kind of a CFT language. Okay. And the second condition, which connects to a question that I received, is that you see that this also allows for, now you have to imagine that this K, maybe we put L, it's clearer that it's lowercase. You see that even if I start with the operator, marginal operator of dimension 2, for a specific theory. When I deform the theory, it might acquire itself an anomalous dimension. It might fail to be marginal in the deformed theory. And this will be controlled by precisely this structure constant coefficient, L, N, I don't know, there will be some delta Ln. And so another condition for marginality is that these vanish. The OPE coefficients or the marginal operators among themselves should also be 0. This is a necessary condition for marginality, for exact marginality. A case that should be very familiar to you where this does not happen is lambda phi to the fourth around the free theory in 4 dimensions. Phi to the fourth is marginal at the free point. As soon as you deform the theory by itself, it acquires an anomalous dimension. And you will be able to see it in this way. Yeah, there are a couple of questions. So.
This looks like a scheme-independent statement,
Mm-hmm.
but this is a scheme-dependent result, the one that you showed.
So the question is...
So are these claims scheme-dependent or not?
Okay. So very good. The question is, of some of the things that you said are, you admitted that they are scheme-dependent, but the exact marginality shouldn't be scheme-dependent. In particular, the vanishing of this OPE coefficient better be not scheme dependent. It should be scheme independent. And this equation itself is scheme independent. And it can be derived in this way. And if you do the computation explicitly, you will see precisely why it is scheme independent. It is because this particular change will come from the logarithmic behavior of the finite part in X. In X itself. So the coefficient of the term of log X in this integrated correlator is what controls this. And no amount of scheme fudging will change the prefactor of the log X. It might change log X into log of 70X, but the prefactor of the log is a well-defined concept. And this will be complete scheme independent, indeed. Yeah, thanks.
Sorry, I'm a bit confused. What do the leftmost symbols mean? Those deltas with the coordinate?
Here?
No, to the left. Yeah.
Sorry, this is supposed to be a Kronecker delta to remind ourselves that this equation is giving us an implicit condition on these OPE coefficients. I don't know if there is a better way to write it down. I just mean that these things on the right-hand side should be 0 whenever K and L are not the same. And right.
Can you repeat the last two questions, where they come from? Are they an assumption?
Oh, this is...
that you are skipping?
I'm asking this as an exercise.
Okay, so it's possible to derive that.
Yeah.
It's not an assumption to which you restrict.
No, so wait. There are two questions. I think that I can interpret your question in two ways. One is this part of the equation an assumption? No, this is a computation. You can compute this. This part will be an assumption from now on. So in any given theory, you will be able to compute these OPE coefficients and check if they are 0 or not. And just telling, if these are 0, then the operator will remain marginal under its own perturbations. So I'm now, this last part here will be an additional condition of marginality. Okay. All right, so if now this part on two-point function is clear, let's move to computing the curvature of this connection. Yes, another question.
From your discussion, it looks like it's not really particular to 2 dimensions apart from a few integration factors. So what persists in higher dimensions?
So the question is, where did you use 2 dimensions in all this discussion?
Yeah. Or what of this structure survives in higher dimension CFT?
Very good. So the question is, what of what I'm saying here survives in higher dimensional CFTs? And the answer is basically everything. Except that, as far as I'm aware, in higher dimensional CFTs, you only have this language of interrelated correlators, and as far as I'm aware, there is no formulation of CFTs in higher dimension based on something like Riemann surfaces and the Sewing conditions. And so while in 2 dimensions, the compatibility of this scheme with conformal invariance can be shown quite easily. In higher dimension, I think you really have to work hard. So that will be the difference. But it's basically the same for the rest. You just have to cut spheres, balls, and all that. OK. So let me move on to the computation of the curvature. So for now, up to now, I'm just telling you, this is a connection because it transforms in the right way, and it might not commute with itself, blah, blah, blah. But you might be worried that maybe this is a trivial connection, a flat connection, and then if I choose my basis of operators carefully, then I don't have to worry about this not being a normal derivative. It's a legitimate, not worry, hope maybe that you might have. And I will now compute the connection, the curvature of this connection. So I will compute it as a tensor. So it will be a tensor that acts on my space of operators. So this is typically what we mean by connection. By the curvature is the commutator of the covariant derivatives. And I will try to tell you how to compute this particular object. And how do you do it? So let's try a guess, right? Let's try, maybe you want to extract this thing in the following way. You do this. You need 2 indices, right? I and j. Well, I raised here 1 index, but who cares? I can keep it low. I can use this 2-point function to raise and lower indices. So you might imagine something like this. Right? That's a natural guess for an object that has this index structure. But before you take pictures of it, this is wrong, right? It's obviously wrong. This is always 0. I just proved it to you, right? This is just the covariant derivative of the GLK and GKL, and I do it just twice, but the second time I just act on 0, so I will always get 0. So clearly, and why is this not correct? Well, because this is not really computing the curvature, right? This is not what we mean by curvature. The curvature computes the following thing. You have to start with an operator, like say phi k. You want to bring it, you want to deform the operator itself in a kind of a square deformations. You go, well, this is way too close. You go in the direction I, you deform your operator, you go in J, then you go back with I, and then you go back with J, and you go back to the original point. And then once you have brought this operator along for the ride, you check how much it has changed. This is the meaning, the geometrical meaning of a curvature. So what we would need to do is something like this. Delta I. This is what we want. But this is a bit outside of the rules of the game that I gave you, right? The meaning of this, whatever it means, I didn't tell you what this means in formula, is that I only apply the covariant derivatives on one of the operators. And after I have brought it along the contour, I compare it with the basis of all the operators. And I compute, this is what will compute the curvature for me. So now my task is to explain to you how to define this operation. Is it clear? Right. So to do this, I will actually use this thing, the state operator correspondence. And this is the first. Right. And so remember the meaning. Let's try to study the state operator correspondence a little bit in more detail. And remember this subject here. And I wrote this as pictorially in this way, right? Phi k equals 0, phi L equals infinity. I raised an index here using this matrix GK, well, the inverse matrix GKL. And the reason is that then this is just the Kronecker delta. It's just easier to work in this basis. And I also told you that this is equal to, well, I didn't tell you, the other lecturers told you that this is equal to this particular inner product of Hilbert space states. But this map between operators and states was a bit abstract, right? Now we want to give a very concrete map, a map that gives us a Schrödinger-like representation for these states. So how do we do this? Well, we have to justify this, we have to go back to our Lagrangian formulation. This is just an intermediate step. We don't really need to, but it's convenient to do so. So in the Lagrangian formulation, this object would also be equal to some path intro. On this sphere, right? And let me not worry about the normalization of these things, it's as usual. So the idea here is that I can think of this as two intervals on two hemispheres. So maybe it's not really in the middle. So the idea here is that I can see this particular operation as doing a path iteration over half of the sphere glued with a path iteration over the other half. So let me do it a bit more explicitly. So I can define an object, right, like a wave function associated with the state k, which will be a function now of the boundary fields on my equator. And this will be just the path iteration of with fixed value of the boundary conditions of e to the minus s, but here let me explicitly restrict the domain of integration to this hemisphere, which is the unit disk when you map it to the plane, the x of L. And I put this operator here at 0. So this is this path integration over half of the sphere is defining for us a wave function on this particular equatorial circle. Yeah, question?
So is there a lambda dependence now or not yet?
Not yet. Is there a lambda dependence? I'm not, no, this is for, I mean, this is the state, the Schrödinger representation of a state for a given value of lambda. And now we'll tell you how to do a lambda deformation of this. Yeah. Right? And why does this particular prescription make sense? Well, maybe I shouldn't write it, but I can do the same thing for the bra, right? I can define. I mean, yeah, so this depends on lambda. All these states are defined for a given theory of lambda, yeah. What I mean is that there is still no lambda change that I'm introducing in this thing. Yeah. So for each value of lambda, this is defining for me a particular state. For each value of lambda in each field phi, this is defining for me a specific wave function, right? And then the bra or the dagger wave function would be just the same, but integrated over the upper hemisphere, right? So this will define for me psi dagger of phi L. And it will also depend on the boundary conditions on the other half hemisphere. So they are not necessarily the same. And when I take the inner product of the two, this is just the standard thing, I have to integrate over all the boundary conditions, like this. This is really standard quantum mechanics. This, maybe I should put a big D, it's a functional integral, but it's the same thing. So this particular thing realizes the state operator map in a very concrete sense. It realizes the states associated to these operators as wave functional. It's probably not very rigorous, but it works very well. And now I can tell you how I can change only one state, right? Now it's clear what I have to do. If I want to change one state and keep the other fixed, I will just have to implement my deformation on one of the two, like the bra or the cat. Maybe the cat is a better idea. So, I used the wrong color. So if I want to define this operation, delta I, psi phi k, b. Now it's just, okay, there is a x xb e to the minus s on the unit disk. Then I have the integrated operator that I use for my change. So there is a minus delta lambda I over 2 pi, and then phi k of 0. But since this particular Lagrangian is integrated on the unit disk, the deformation itself is integrated on the unit disk. So here I restrict my domain of integration to the unit disk. And now it's clear that this operation, so phi k will just be very similar to my prescription for my previous prescription for the deformation of the correlators. So d2y phi L infinity O I y phi k of 0. The usual prescriptions apply in the sense that I have to make sure that the operators do not sit on top of the singularities. But the additional condition is that this is taken on the unit disk. Question? Yeah. Sorry. You're right. Then I either put the d lambda I on both sides or I don't put it at all. Thank you. Yeah, so I was, yeah. This is the prescription for the integrated correlator. And of course, now you can see that the only possible singularity comes from from the operator at the origin. So I have to cut a small disk around that, and then remove the singularities and all that. But I don't have to worry about the operator at infinity. So this, and now we are out of time. So tomorrow we will see that we can use this technical tool to compute the curvature, because now we have understood how to pool derivatives inside the correlators themselves. And yeah, we'll continue tomorrow with this.
Questions? I have to have one.
Yeah.
To start. That thing looks suspiciously similar to how you were actually computing the previous, the variation of just the two-point function. I mean, if you replace that one with one over epsilon, I guess.
Yeah. So the comment is the following. The comment is, this formula that I wrote is suspiciously similar to the one where I compute the variation of the two-point function. The only difference is that I'm restricting the domain of integration to the unit disk. Right? Well, this is a comment, not a question, right? So
I was wondering whether, I mean, it seems that if you change your regularization scheme, you say that one point has to be regularized with some epsilon and one with some other epsilon, then you get your original formula to this one, which sounds a little bit confusing.
So sorry. So I cannot repeat the question because
So,
it's.
what I'm saying is that when you have smaller than one, if you wrote 1 over epsilon there,
Yeah.
that would be the previous formula. If you now have epsilon 1 and epsilon 2, and you decide that one epsilon is epsilon 1, that is exactly this.
Yeah. So actually, tomorrow we will compute this and see that there is no such ambiguity that you have in mind. There is some possible confusion if I do this operation and then I do the same operation on the bra, but I do it with a different disk, and then I glue back the result together. Should I get the computation that I did before? You do. You can show this. So it actually works. So maybe I should also add the comment that, well, okay, that's fine. I will add it tomorrow. More questions?
What is the finite piece of that integral?
What is the finite piece of that integral? Yeah, so you can, yeah, so due to lack of time, I plan to write the formula directly for the curvature, but I'm showing you a simpler formula for this object. And you're asking what is the finite piece, and you're basically anticipating something that I will do tomorrow when I talk about the Berry phase. And indeed, if these two operators have the same conformal dimension, then the finite piece will be actually 0. And so, but this is fine. I will show you that this is a completely meaningful and consistent result. Actually, exactly what we want. So it's good. Yeah.